Step into this confined steel enclosure. Sense the pressure of 45 tons bearing down through narrow tracks. Your hands clutch controls that respond sluggishly, like syrup in winter. The engine roars behind you, a moody beast that could stall at any moment. Welcome to the Panther, Germany's so-called superior tank. The same machine that broke down more often than it engaged in combat. The same vehicle that spent more time in workshops than on battlefields. What Allied soldiers discovered inside these captured German marvels would shatter every assumption about tank warfare and alter our understanding of one of history's greatest engineering debates. December 1944, the snow-laden forests of the Ardennes. American tank crews huddled in their Shermans, watching German armor emerge through the mist. Panthers, the sleek predators of the battlefield, 45 tons of sloped armor, and a 75mm high-velocity gun. Every American tanker had heard the tales. One Panther could take on 5 Shermans. The German tank's frontal glacis armor was 80mm thick at 55 degrees, providing effective protection equivalent to 139mm. Its turret front measured 100mm. Its KWK-42 L-70 gun could penetrate a Sherman from more than 2,000 meters away. American tankers grimly referred to their own vehicles as Ronsons, after the cigarette lighter, lights every time. The crews, climbing into their 33-ton Shermans that frigid morning, knew the statistics. They knew the Panther outgunned them. They were aware its armor could deflect their 75mm rounds from the front. They understood that in a direct fight at long range, they were outmatched. The German tankers knew it too. They had been told their Panthers were unbeatable, that American tanks were inferior in every way. Their propaganda films depicted Panthers crushing Sherman after Sherman, German steel triumphing over American mass production. The Panther had been designed specifically to counter the Soviet T-34. After German forces encountered T-34s during Operation Barbarossa in 1941, particularly at the Battle of Mtsensk in October 1941, German High Command immediately dispatched a special armor investigation committee. The Panther Commission formed in November 1941. Mann's design was selected in May 1942. The first prototype appeared in September 1942. Production began in January 1943. On paper, it was perfect, the ultimate medium tank. Nearly every technical specification favored the German machine. But something peculiar started happening as American forces pushed deeper into German territory. Tank recovery teams began finding abandoned Panthers. Not knocked out by enemy fire, not disabled by mines, simply left behind by their crews. Engines cold, fuel tanks still containing diesel, transmissions locked up, final drives shattered. Some Allied forces did capture and attempt to use Panthers. The British Coldstream Guards famously operated a Panther they named Cuckoo during fighting at Geilenkirchen Castle in late 1944 and Operation Blackcock in January 1945. Canadian forces captured an intact Panther in Italy in October 1944, called it the Deserter, and used it in multiple assaults before sending it for study. Polish resistance fighters captured 2 Panthers during the Warsaw Uprising in August 1944. They used them to destroy German machine gun nests and to liberate the Gęziowka concentration camp, freeing 348 prisoners. But within days, both Panthers were immobilized due to lack of fuel and batteries and had to be set on fire to prevent recapture. The pattern was consistent. Captured Panthers could fight brilliantly for short periods. Then they broke down. The British, who built 9 Panthers post-war using German parts and technicians, tried to conduct standard acceptance trials in 1947. They could not complete the trials. The Panthers kept breaking down. The British report concluded that very little information of any value was obtained due to the general mechanical unreliability of the Panther. The French Army, which operated Panther units post-war using captured vehicles, conducted the most thorough evaluation. Their 1947 technical report, titled Le Panther, stated directly, "The truly weak spot of the Panther is its final drive, which is of too weak a design and has an average fatigue life of only 150 kilometers. Let that sink in. 150 kilometer, less than 100 miles before the final drives. The units that transferred power from the transmission to the tracks needed complete replacement." German wartime documents confirmed this catastrophic failure rate. General Guderian wrote in June 1944, "The lifespan of the Panther's motors, 1/400 to 1/500 kilometer, is significantly higher than the Panther's final drives. A solution to the final drive problem is urgently needed." An Eastern Front report from March to April 1944 documented that since the 1st of March, 13 final drives were replaced in 30 Panthers. A January 1945 Panzer Commission report listed 370 defective final drives from Panthers requiring replacement. Half of all Panthers abandoned in Normandy showed final drive failures as the primary mechanical issue. The technical cause was well understood. Mann's original design called for epicyclic planetary gearing. This was changed to a double spur gear system due to gear-cutting machinery shortages in German industry. The double spur gears had inherently higher internal impact and stress loads. Here was the fatal flaw. The Panther's drivetrain had been designed for a 30 to 35-ton tank, but Hitler demanded extra armor and a heavier gun during development. The final production, Panther weighed 45 tons. The final drive housings, designed for a lighter vehicle, simply could not handle the actual combat weight. The housings flexed under load, and the gears inside bound up and destroyed themselves. Sherman final drives, by contrast, could operate for thousands of kilometers without major maintenance. French operational experience from 1946 to 1950 with their captured Panther units confirmed the 150 kilometer failure rate repeatedly. The Maybach HL230 engine, while powerful at 690 horsepower, suffered chronic reliability problems. During Operation Citadel at Kursk in July 1943, Panzer Abteilung 54 experienced 20 fuel pump failures by July 8th. Fuel leaks from these failures caused 3 Panthers to become total losses due to engine fires. 2 Panthers from the initial deployment burned out from engine fires just getting off the trains before the battle even began. Documented Maybach engine problems included cylinder head gasket failures, connecting rod breakage, oil pump drive shaft breakage, engine fires from oil leaks onto hot exhaust manifolds, cooling fan drive, bearing failures, and chronic overheating. The Germans derated the engine from 3,000 RPM to 2,500 RPM in November 1943 to extend engine lifespan. This reduced maximum speed from 34 mph to 28 mph and power output from 700 to 580 horsepower. Even after these derating measures, average Maybach engine life in Panthers was only 1,000 kilometers, according to the French post-war technical report, with maximum life reaching 400 to 1,800 km in some cases. The Panther's turret traverse system added another layer of complexity. Early AUSF-D models used a single-speed hydraulic system requiring approximately 60 seconds for a full 360-degree rotation. Later AUF A and G models featured selectable high and low gear ratios. At 2,500 RPM in high gear, the turret could traverse in 17 to 18 seconds. At low RPM or in low gear, traverse time extended to 60 to 93 seconds. The system's performance varied constantly with engine speed. If the engine died, the turret could not traverse at all. The Sherman, by contrast, used an independent auxiliary electric motor. The Sherman's turret always rotated in 15 seconds regardless of engine speed. The commander could traverse the turret even with the main engine off using the backup generator. This consistency provided enormous tactical advantages. The Panthers' theoretically faster traverse at optimal engine speed was meaningless when mechanical failures stopped the engine or when tactical situations required turret movement while the engine idled. The 7-speed manual transmission was stiff and difficult to shift. Every gear change was a battle. Sherman transmissions were smooth and nearly automatic in operation. The Panther's narrow track width, despite good ground pressure on paper, meant less actual contact with soft ground. In mud or snow, Panthers frequently became stuck. Their excellent cross-country performance applied only to firm, dry terrain. The Sherman's wider tracks provided superior real-world traction in varied conditions. Crew ergonomics in the Panther were poor. The interior was dark and cramped. The gunner's position was more confined than in a Sherman. The loader had to reach across the large gun breech in awkward positions to access ammunition scattered around the fighting compartment. The Sherman's ammunition storage featured ready racks within easy reach of the loader. Everything was organized logically. American automotive engineers had designed the Sherman using the same human factors principles they applied to automobiles. Make it easy for the operator. By March of 1945, the complaints from American tankers about facing Panthers and Tigers had reached General Eisenhower repeatedly. He wrote to the commanding generals of the 2nd and 3rd Armored Divisions asking for detailed assessments. General White, commander of the 2nd Armored Division, prefaced his reply by asking Eisenhower to make allowances for the traditional enthusiasm displayed by the American soldier when given the opportunity to express himself regarding any possible shortcomings in his equipment. General Collier, commander of Combat Command A of the 2nd Armored Division, provided a detailed assessment. The consensus of opinion of all personnel in the 66th Armored Regiment is that the German tank and anti-tank weapons are far superior to the American in the following categories: superior flotation, greater mobility, better gun sights, and higher velocity guns. Smokeless powder that made German tanks harder to spot. Better sloped armor and better silhouette. Collier then contested Eisenhower's rationalization that American equipment limitations were justified by shipping distances. The fact that our equipment must be shipped over long distances does not, in the opinion of our tankers, justify our inferiority. This was March 1945. The war in Europe would end in May. Eisenhower replied immediately, "I feel that your conclusions should go at once to the War Department, and I am sending them on to General Marshall without delay." Too late for any changes to affect the outcome, but these documented assessments reveal that American tankers clearly recognized the Panthers' advantages in direct combat. They wanted better tanks. They were not blind to the Sherman's limitations. Yet, they won anyway. Not despite the Sherman, but because of what the Sherman represented, a complete weapon system optimized for total war. Between June and December 1944, the 12th Army Group lost more than 2,000 medium tanks, mostly Shermans. These losses shocked the American public when soldiers' letters home and press reports revealed the scale of tank casualties. In January 1945, New York Times correspondent Hanson Baldwin wrote critical editorials urging congressional inquiry into American tank adequacy. The Army leadership responded with articles defending the Sherman. Major General Levin H. Campbell, Jr., Chief of Ordnance, released Eisenhower's letter to diffuse further criticism. After the war, General Marshall tried to explain American tank performance, acknowledging that from summer 1943 to spring 1945, German Tigers and Panthers outmatched Shermans in direct combat. But Marshall's explanation emphasized that American doctrine never intended for medium tanks to fight heavy tanks alone. Tank destroyers, artillery, and air support were meant to neutralize heavy armor, while medium tanks performed their primary role of exploiting breakthroughs and supporting infantry. Though Sherman's combat record, examined beyond individual engagements, demonstrates overall effectiveness. American and British forces landed in Normandy in June 1944. By May 1945, 11 months later, Allied armies had advanced from the French coast to Berlin, conquered Germany, and ended the war in Europe. German forces equipped with technically superior armor could not stop this advance, not because Panthers and Tigers were ineffective in battle, they were deadly when they fought, but because they could not fight consistently enough to matter strategically. A tank that breaks down before reaching battle provides zero combat power. A tank immobilized by lack of fuel contributes nothing. A tank awaiting spare parts that never arrive becomes a stationary pillbox. Strategic effect requires sustained operations over time and distance. The Sherman provided sustained operations. The Panther did not. The Sherman succeeded because it prioritized the right factors, not gun penetration at maximum range, not armor thickness in frontal engagements, but reliability, maintainability, crew survivability, production capacity, logistical sustainability, and tactical flexibility. Consider the Sherman's 5-man crew layout. Commander, gunner, loader, driver, assistant driver, who also operated the bow machine gun. The crew positions allowed efficient operation and good crew coordination. Multiple escape routes included a large belly hatch, side hatches, and turret hatches. When a Sherman was hit, crews had excellent chances of escaping. The British, after studying captured Tiger 131, used its technical details to help design the Sherman Firefly with the 17-pounder gun. Sherman variants addressed different tactical needs. The M4A3E2 Jumbo featured 102 mm Glacis armor and 152 mm turret front armor. Fisher Tank Arsenal produced 254 Jumbos from May to July 1944. These were deployed as breakthrough tanks to lead assaults. The wet ammunition storage system introduced in Sherman production placed ammunition in water glycol jacketed bins. This reduced fire probability when penetrated from 60 to 80% down to 10 to 15%. This single improvement saved thousands of crew lives. The 76 mm M1 gun, introduced in January 1944 and first seeing combat in July 1944 during Operation Cobra, provided improved armor penetration. However, the 76 mm gun had significantly worse high explosive performance than the 75 mm. The 75 mm M48 round produced 950 effective fragments in a 20 FT radius. According to U.S. Army Technical Manual 9/1907, the 76 mm one produced only 560 fragments. The reduction in HE effectiveness was a real tactical limitation that many units preferred to avoid. American tankers understood that tanks fought infantry far more often than they fought other tanks. High explosive effectiveness mattered more in most combat situations than armor-penetrating capability. The Panther's KWK 42 L70 gun, optimized for anti-armor performance with its high velocity and long barrel, fired a weaker HE shell compared to lower velocity weapons. High-velocity long barrel guns sacrifice explosive effectiveness for armor penetration. You cannot optimize for both simultaneously. Israeli forces recognized the Sherman's fundamental soundness. They modified, captured, and purchased Shermans extensively. The M50 Sherman, with a French 75 mm gun and Continental R975 engine, served from the 1956 Suez Crisis through the 1967 Six-Day War and the 1973 Yom Kippur War. The M50 Continental Mark I retired in 1972. The M50 Cummins Mark II served into the late 1970s. The M51 Sherman mounted a French 105 mm gun. It served from 1965 into the early 1980s. Israeli M51 successfully engaged modern Soviet T-54, T-55, and T-62 tanks using 105mm heat rounds. Israel sold 75 M51s to Lebanese militias in 1976 and over 100 to Chile, which used them until 1999 and kept some in reserves until 2006. This operational longevity from World War II through the 1970s and 80s demonstrates the Sherman's fundamental design, soundness, and adaptability. Now, consider the Panther's systemic failures. Production totaled approximately 6,000 vehicles between January 1943 and March 1945, not 9,000, as commonly stated. Several authoritative sources confirm that par 6,000 is the accurate number of Panthers produced, with some sources citing 5,064 vehicles built. Peak monthly Panther production reached 380 units in July 1944, but the average output was significantly lower. Frontline strength peaked on postwar in September 1944, with 234 tanks. However, that same month saw us record losses of 692 tanks. The final operational report, dated final 15th of March 1945, showed that out of my 7040 Panthers on the battlefield, only my 3061 remained operational. By the end of the war, only 49% were still in service. Allied bombing campaigns deliberately targeted Panther production facilities. Daimler-Benz plants were bombed on August 6 and 23 August 1944. So, the Wyman factory was struck on September 3 and 19 October 1944, and again on January, and 21 February 1945. These raids sharply reduced spare parts production from 30% of tank output in 1943 to just 8% by the end of 1944 FIO. On the battlefield, Panthers were often cannibalized for parts to keep other vehicles operational. The shortage of spare parts further worsened mechanical reliability problems. The quality of German crew training deteriorated sharply as the war progressed. Historian Steven Zaloga noted that the disappointing performance of Panthers in the Ardennes against American Shermans, despite superior technical specifications, was largely due to the poor quality of crews at that stage of the war. Most Panther crews were inexperienced and received only minimal training. This lack of training compounded the Panther's technical weaknesses. The combination of unreliable transmissions, fuel shortages, a lack of spare parts, and inexperienced crews resulted in many Panthers breaking down and becoming irreparable. Babar, French report from 1947, concluded that poor driver training was the primary cause of Panther mechanical failures. Crews were often assigned drivers who were operating a Panther for the first time. Tanks were written off due to relatively minor technical issues. Fuel shortages paralyzed German armored operations. Panthers consumed enormous amounts of fuel, and German logistics were unable to sustain fuel deliveries to frontline units. Soviet tanker Dmitry Loza, a hero of the Soviet Union, commanded American Shermans on the Eastern Front. He documented his experience in the book Commanding Sherman Tanks in the Red Army. In an interview, Loza stated, "The service life of Sherman tracks exceeded 5,000 kilometers." He praised the Sherman's reliability, highlighting the auxiliary gasoline engine used to charge the batteries, which eliminated the need to run the main 500 horsepower engine. Loza also noted the high quality of American armor, which did not produce internal spalling, the comfortable crew positions, and overall mechanical reliability. He remarked that the Sherman handled like a car on hard surfaces, whereas the T-34 made so much noise that only the devil knows how far away it could be heard. The suspension system used vertical vollet spring blocks, which were simple and reliable, allowing production by companies with no prior military experience. Every design choice reflected the priority of mass production without the need for specialized tools or methods. Training new tank crews in the Sherman took approximately 13 weeks at armored training centers. The layout was intuitive for men familiar with automotive equipment, and the controls responded predictably. The maintenance procedures documented in clear technical manuals could be learned by mechanics with a basic automotive background. In contrast, German Panther training required longer periods and more specialized instruction due to the vehicle's complexity. As German losses mounted and training time shortened, crew quality declined. Meanwhile, the American training pipeline maintained consistent standards throughout the war, producing adequately trained crews at the rate operations demanded. The advantages of the Sherman's maintenance became evident in prolonged operations. A typical engine change for a Sherman took between 8 to 10 hours with a skilled team and the right tools. The power pack, engine, and transmission could be removed and replaced as a single unit. Armored divisions carried spare power packs on trucks that followed advancing tank columns, enabling a disabled Sherman to return to action within hours. In contrast, removing the Panther's engine required significantly more time and specialized equipment. The engine and a transmission were separate components, each needing its own removal process. Field maintenance of Panthers often proved unfeasible, necessitating towing tanks over long distances to depot-level facilities. Many Panthers were abandoned after relatively minor failures because field repair was impractical. Sherman track replacement could be done by the crew in the field in 3 to 4 hours per side. The track blocks were relatively lightweight and manageable by 2 men. Panther tracks were heavier and more challenging to handle. The interleaved road wheel system, while providing excellent ride quality, meant that if an inner road wheel was damaged, multiple outer wheels had to be removed first to access it. In winter conditions, mud and snow froze between the interleaved wheels, immobilizing Panthers until extensive deicing efforts were completed. Shermans, with their simpler suspension and independently mounted road wheels, did not suffer from this vulnerability. The logistic support for Sherman operations was extensive but manageable. Each armored division required thousands of tons of fuel, ammunition, spare parts, and supplies monthly. American logistics units reliably delivered these supplies over increasing distances as armies advanced through Europe. The Red Ball Express, a truck convoy system, delivered 7,000 tons of supplies daily at its peak. Liberty ships transported material from American factories across the Atlantic. The logistics system was effective because it was planned, resourced, and executed as an integrated whole. German logistics, by contrast, collapsed as Allied bombing destroyed rail networks, fuel production facilities, and transportation infrastructure. Even when Panthers were mechanically sound, a lack of fuel immobilized them. Sherman fuel consumption, while substantial, remained within logistical sustainability. Combat operations consumed fuel at high rates, but American logistics could continuously deliver sufficient supplies. Panthers consumed fuel at similar or higher rates, but German logistics couldn't maintain supply. The difference was not in vehicle consumption, but in logistics system capacity. American logistics was built to support mechanized warfare on a global scale across ocean supply lines. German logistics was designed for relatively short campaigns within Europe and collapsed under prolonged operations and Allied interdiction. The Sherman succeeded because it was designed, produced, and employed as part of a complete military system. The Panther failed because it was designed as a technically superior weapon without adequate consideration for the system required to sustain it in combat. Wars are fought by systems, not by weapons. The side with the better system wins, even when the enemy has better weapons. The United States in World War II built and sustained a military system capable of projecting power globally, supplying forces across oceans, maintaining equipment in harsh conditions, training replacement personnel continuously, and adapting doctrine to changing circumstances. Germany built increasingly sophisticated weapons that its industrial base could not produce in adequate numbers. Its logistics network could not sustain in the field. Its training pipeline could not provide adequate crews for, and its tactical doctrine could not employ effectively given declining resources. Post-war analysis by military professionals confirmed these conclusions. The French Army, operating captured Panthers from 1946 to 1950 in the 5001st and 5003rd Armored Regiments, documented every mechanical failure and operational limitation. Their 1947 technical report, Lee Panther, became the definitive assessment of the vehicle's true performance under sustained military operations. The report confirmed the 150-kilo final drive life, the 1,000-kilo engine life, the maintenance difficulties, the fuel consumption, the crew discomfort, and the tactical limitations. French engineers and tankers, initially impressed by the Panther's specifications, concluded that the Sherman was the superior combat vehicle when all factors were considered. They noted that while certain Panther features were admirable, particularly the gun and optical equipment, the overall package was unsuitable for sustained military operations. The British post-war evaluation reached similar conclusions. British forces captured numerous Panthers during the campaign in northwest Europe. After the German surrender, British authorities commandeered a German Panther assembly facility at Hanover and forced the completion of 9 additional Panthers using existing components and German technicians. These 9 British-built Panthers, completed in spring 1946, were intended for comprehensive testing. Standard British armored vehicle acceptance trials were conducted on 2 Panthers and 2 Jagd Panthers. The trials had to be halted when the last working Panther damaged its transmission during a hill-climbing test. All other Panthers had already been cannibalized for spare parts or had broken down from mechanical failures. The conclusive report, dated February 1948, stated that very little information of any value was obtained, noting the reason as the general mechanical unreliability of the Panther and Jagd Panther tanks. Britain, like France, found that captured Panthers were interesting technically, but useless operationally. American testing at Aberdeen Proving Ground in Maryland examined captured Panthers, though detailed public reports comparable to the French assessment have not been widely published. Multiple Panthers were documented at the U.S. Army Ordnance Museum at Aberdeen. The facility specifically examined captured enemy equipment from every battlefront. American engineers recognized the Panther's advanced features, but also documented its numerous flaws. The knowledge gained influenced post-war American tank development, though not by copying Panther systems. Rather, American engineers learned what not to do, how over-optimization for specific parameters creates systems that fail under operational stress, how complexity without corresponding reliability produces unusable weapons, and how impressive specifications mean nothing if the vehicle cannot be sustained in combat. The developmental dead end of the Panther contrasts sharply with the Sherman's evolutionary success. Many World War II weapon systems continued in service for decades or influenced post-war development significantly. The German Me-109 fighter was produced and developed by Spain and Czechoslovakia into the early 1960s. Mauser rifles remained in service with numerous armies post-war, but the Panther vanished. No nation adopted it for post-war service once captured stocks and spare parts were exhausted. The Soviets, who captured hundreds of Panthers, used them briefly, then discarded them. Czechoslovakia and other Eastern European nations that operated captured Panthers in the immediate post-war period quickly replaced them with Soviet designs. France and Britain, after thorough evaluation, concluded the Panther was not worth continued operation. The design influenced no subsequent tank development in any meaningful way. The Sherman, by contrast, evolved continuously. The basic M4 platform was adapted for dozens of specialized roles. Tank recovery vehicles, armored personnel carriers, self-propelled artillery, rocket launchers, bridge layers, mine clearers, and flamethrowers all use the Sherman chassis. The adaptability of the design allowed it to serve in roles far beyond its original purpose. Israeli modifications produced vehicles that fought successfully in the 1960s and 70s against Soviet-designed armor. The M50 and M51 represented comprehensive rebuilds that retained only the basic hull while upgrading every system. These Israeli Shermans mounted French cannons, American or British engines, improved suspension, modernized fire control systems, and enhanced armor. They proved that the fundamental Sherman design was sound enough to accept decades of improvements. The Panther's design allowed no such evolution. Its complexity and tight integration meant modifications were impractical. The vehicle was optimized for its original configuration and could not adapt. The Sherman represents one of history's most successful weapon systems, not because it was perfect, not because it was the best tank by any single metric, but because it was good enough, reliable enough, maintainable enough, producible enough, and trusted enough by the crews who fought in it. That combination of adequate technical capability with superior systemic factors created a weapon that won the war. The Panther represents a cautionary tale about the limits of technical superiority. Impressive specifications matter little when the weapon cannot reach the battlefield, cannot be sustained in combat, cannot be produced in adequate numbers, and cannot be operated effectively by available crews. Technical excellence divorced from systemic requirements produces expensive, unreliable, unsustainable failures, no matter how impressive the design appears on paper. History has delivered its verdict. The Sherman won. The Panther lost. Not in any single engagement, but in the campaign that mattered, the production battle, the logistics battle, the sustainability battle, the reliability battle. American tankers understood this. They lived it. They fought in it. They won because of it. 79 years later, the lesson remains clear. Wars are won by systems, not by weapons. The side that builds the better system, even with adequate rather than superior weapons, defeats the side with superior weapons but inadequate systems. The Sherman versus Panther debate ended in May 1945 when American Shermans rolled through Berlin while abandoned Panthers littered the roads behind the retreating German army. The debate never should have existed. The answer was always obvious to those who understood that effectiveness in war is measured not by specifications but by results.